Okay, good afternoon, 61C. Good afternoon. Okay, good to see you again. So today, we're going to be talking about virtual memory in a bit more depth. Just to recap, last time Martin told you about something about programmed I/O, polling versus interrupts, asynchronous interrupts versus synchronous traps, precise interrupts, and a bit about virtual memory. I'm going to go over that again, some of this stuff a bit more slowly again, review that today. It takes a while to get your head around virtual memory. I believe we find it takes people about 3 classes worth of virtual memory before it kind of sticks. So don't worry if you feel like you're getting lost. We're trying to explain what you need to know for this semester. So where we are is right in the middle of the core. This is all things that happen right by the processor, a single processor inside the system. Now let's dive off and talk a bit about traps, interrupts, and exceptions. So, most of the course we've just been talking about the processor as if it starts running a program and keeps running the program until end of eternity or until you found the answer to the problem set question. That's a very simple view of how processors operate. Out in the real world, processors are continually being interrupted by different events. So they're trying to run a program, and something happens that needs the processor's attention. You need to run some other bit of software to handle something that's happened outside. And the mechanism we use in the computer is called an interrupt to report things from the outside. There's actually not just interrupts from outside, there are also events that occur during execution of a program. Like something about this instruction in this piece of code that I'm currently executing needs me to go do something different than just finish executing that instruction. So one example will be for virtual memory, where you try and do a load from a memory address that's actually not present in the machine right now. And what you're going to have to do is take a trap, stop executing that instruction, jump into the operating system, have the operating system go actually retrieve the data from disk, bring it into memory. So many, many things will happen before I go back and actually resume and try and redo that load instruction. So that's an example of an exception where something happened in some program I was running that was related to what each instruction was trying to do. But the general thing for all interrupts and exceptions is when they take place, we have what's called the trap handling, where some event happens, either an external event like an interrupt or an internal event like some exception is raised, and you need to automatically jump to some other piece of code that isn't in the main program you've written and do something else there. So you want to divert in this diagram, you have the processor executing this instruction. On this instruction, we're going to take a trap. And that means we sort of jump off to the side and go to a different PC. So the program counter gets changed, and you sort of, all of a sudden, you're shifted off to this other world where you're running this other piece of code. So the software over here is called the trap handler. It deals with this trap that happened, and generally will then just come back and resume execution back at where you left off. Not always. Sometimes that event will cause you to do something different than continue execution. But quite often you'll go back and resume executing the same program. And these are called traps, interrupts, exceptions. I'll talk about our terminology. People mix these terms up a little. But they're all related to unusual events. They're not the normal or in the mill thing. Something unusual happened, and we handle it in this way. All right. So this is our terminology slide. So this is the terms I prefer to use. You'll see these written differently in different places, and IBM will have it backwards as always. But basically, an interrupt is something outside of the current program. That's the way I use it. So something else is seeking the processor's attention. An example is to be like when you press a key on the keyboard, you want to stop the program from doing what it's doing and pay attention to your key press, or if you have some mouse activity. So some kind of I/O device is a classic case of an interrupt. Right, the program's running one thing, I want to tell it to go do something else temporarily. And that's unrelated to the program that's currently running. And the nice thing about that is that when you're building the machinery, you can choose to take that interrupt on any instruction that's convenient. You can wait to a convenient place to go handle this external event. Another kind of event that happens when you're executing code is an exception. An exception is something to do with an instruction in the program. So an example would be a page fault, which we'll talk a bit more about, or say an illegal instruction. Like you run your code and you hit some instruction that is illegal for your machine. You want to trap and tell the user the program's broken, that something's wrong with the program. Now these are different than interrupts because these are related to the code you're running. There's something about the program you're actually running will cause you to hit that exception. And if you run the program again, you'll probably hit the same exception, right? It's something to do with the program you're currently running. That's an exception. Now, I use the term trap to refer to how you actually action something, either an exception or interrupt. When you take a trap, is a terminology. That's the action of servicing that event, and you jump to a piece of code that will call the trap handler, right? So you invoke a trap either on an interrupt or an exception. The trap is the thing actually happening, and then you'll go and execute some trap handler code to deal with the event, whatever it was. Okay, so interrupts, asynchronous to the current program, something to do with outside. Exception, something about the program you're currently running, and it's synchronous to the program. It occurs on a given instruction, and you have to take it on that instruction. Like if an exception occurs for an illegal instruction, you don't keep going for the 100 instructions and then take an exception. You want to deal with it as you encounter it on the specific instruction that caused that exception, right? That makes it actually a lot harder to implement in the hardware. And finally, a trap is just a general term for dealing with one of these things as they occur in the machine. Now, it turns out over time, many things have been tried and proposed, but the sort of pattern that people like to keep coming back to is the notion of providing precise traps on a machine. So there's many different ways you could do traps, but the one that seems to be successful, even though it's harder to do, is the notion of a precise trap. And a precise trap is one where it's like you stop cleanly on one instruction. So remember, the programmer's model, the ISA, is all written in terms of single sequential instructions. Like you execute this instruction, this is its behavior, this is how it's going to affect the registers. Then I move to the next instruction, and I do all of that instruction. So the simple sequential model is part of the ISA contract you have with software. And we saw already that we have to be careful when we build a pipeline processor, that even though we're overlapping execution of instructions, we make it look as if each one finished before the next one started. So you could use the result of one instruction to the next instruction. A precise trap extends that to how exceptions are handled, so that when something goes wrong in the program, you want to make it look as if you stopped dead on one instruction and everything before that finished, and nothing after that had any impact on state, and it's just a clean break at this one instruction, right? So if I go back to this diagram, you want to make it a precise trap is one where everything previous to this instruction is finished, and so any writes to memory, any updates to the registers are seen by any following code. Nothing that's happening in these following instructions affects the machine in any way. It's as if they never happened. And so when you get to this first instruction, the trap handler, there's a special register inside the processor you can read, which points at the PC of the instruction that caused the trap. And in MIPS, this is called the EPC, exception PC, right? So the pointer, this trap handler can read this special register that says, where did that happen? Where did this go wrong? And it points at exactly one instruction, right? And this handler, if it saves all the registers and restores all the registers and jumps back to that program counter, it'll be as if nothing happened, the original program. That's one of the goals of a precise trap, that all you have to do to recover from it is to save all the state, the registers, and this error PC, and jump back to the error PC and keep going, right? And so the interrupt handler, if you're handling just an interrupt, which remember is completely independent to the program you're running, the interrupt handler, all it has to do is save the registers that the user has and remember that PC. And when it wants to come back to the same piece of code, it just reloads the registers and jumps to that PC, and the program continues from where it left off. Right? And so all that, as far as the program's concerned, they just lost some time. Something happened and it lost some time. But functionally, it's identical as if the interrupt never happened. Right? So the precise trap makes this easy because it's just all you have to know is which instruction caused the trap. Now, you might say, well, that's the obvious thing to do, like just stop on one instruction. However, when you build a pipeline implementation, as we'll talk about in a minute, you may have many instructions in flight, and if you have a pipeline processor, superscalar, and out of order, you may have many instructions on the go from different points in the program, and this actually takes a lot of effort in the microarchitecture to unravel it all to make it look like it's precise. But it turns out over time, even though architects tried to foist this onto software, you deal with the imprecise interrupts, software guy says, no, that's basically impossible. You have to give me a precise trap at the hardware level, and so I have this nice simple model for software to deal with. Okay, so basically it's hard to do this in a complex processor, provided precise traps, but it's even worse to try and deal with it in software if you don't have precise traps. So a very simple model. Trap occurs, you point out one instruction, that was the culprit. Do the handler, you can just restore back at that one instruction. Very clean. That's a precise trap. So let's talk about, even for our simple 5-stage pipeline processor we've been developing, let's think about how we handle traps in here. And so remember, there are two kinds of things that cause traps. One is interrupts from outside, And the other one is exception. Something's gone wrong with the current program that's executing. So the way it looks in the pipeline is, when I have the program counter here go into instruction memory, I may have some circuitry that's checking that program counter to say, is this a legal program counter? Is it a valid program address? Am I allowed to execute code from here? And if not, you'll get a PC address exception saying, that's not a legal program counter. You shouldn't have been trying to execute code from there. If it is legal, when I go into the instruction memory, I may fetch an instruction and find out, wow, this is not a valid instruction. This is an illegal opcode. You shouldn't be trying to run this code. So you want the machine to report a legal opcode exception. Or in MIPS, you'll see that the add instruction actually causes an overflow exception if the integers overflow the 32 bits. And so in the ALU stage, in the execute stage, you might get an overflow exception, okay? And then going down the pipeline even further, say this was a load instruction, you calculate the load address, and then you check that load address, and you might find out, oh, this is an illegal address. It may be a misaligned address for a load word, for example. That's illegal. So you want to raise a data address exception. So each of the different phases of execution of the instruction can generate different kinds of exception about that instruction that's going through the pipeline, okay? All right, so now the tricky thing is on one clock cycle, your pipeline can be full of instructions, and you might have interrupts coming in, and all this happens simultaneously. It's like, well, what do I do? I've got a PC exception, a legal opcode exception, an overflow exception, a data address exception, and an interrupt. What do you do? What should you do? Any thoughts? Okay, say you didn't have an interrupt. Which exception should I handle if all of them show up at the same time? Data address. Why the data address? It's the first instruction, right. So you want to service the data address exception because it's the oldest instruction in the machine. It's the one that was, oldest in program order. So, originally I fetched and executed this guy. This one came after one, this one came after, this one came after. Those are later instructions following it down the pipeline. And if you think about the precise exception model, I want to make it appear as if everything happened up to the instruction that caused the exception and nothing after it, right? And also I finished all the instructions prior to the one that causes the trap. So I want to make sure that there's no older instruction is going to cause a trap. But here, I know that this one is definitely older than these guys, so I should do this one first, right? Another reason to do the oldest instructions first is that that exception may mean all the other exceptions are kind of just a consequence of that first thing going wrong, right? So this was some bad thing happened here, then all these other things were just a consequence of running off into some bad place in the code. So you just want to report the first place where things go wrong, right? That's another way of thinking about it. Okay, so if all these happened on the same time, you would pick the oldest one to have happen. Let's look at a slightly different problem. What if on one clock cycle I get a legal PC address, okay, and on the next clock cycle I get an overflow? So the first clock cycle I got a PC exception, the second clock cycle I got an overflow. Which of those two should I handle first? You might think, well, if an exception shows up, I should just take care of it. Yep. So that's a question. So if on one cycle the PC overflow, should I just go ahead as soon as I see an exception? Should I service this exception at this stage in the pipeline? How could it be that I would, a cycle later, get an overflow exception? What would that mean?
That instruction was one before, like it was already at state 2.
Right, so if I have on one cycle this is causing a PC error, there's some instruction here, the next cycle this instruction moves to here and causes an overflow, right? And what you realize is if I just immediately serviced the PC exception as soon as I saw it, I may end up servicing exceptions out of order, which I don't want to do, right? Because there might be an older instruction in the pipeline that hasn't got to the part of the pipeline where it's going to report the exception that's going to make it go wrong, right? So say I had a bad PC address, but then I had an ALU operation here, an add operation. This went bad, but I want to actually report the overflow on this before I do with the PC instruction. So I don't want to report the PC exception straight away. I want to wait so I can report all the exceptions in order that they might occur in the program. So you want to report them in the same order they would occur if you did one instruction at a time, sequentially. Yep.
So in general, like if you have like a certain amount of like exceptions, you just want to pick the one that would happen the latest.
Right.
That meant it would happen first.
Happen first. Yeah, you want to pick the exceptions. You want to report them in the same order they would happen if you just did it in program order. The way the assembly level programmer is looking at the code and they're following execution, they should happen as if it happened. You did all of one instruction, figured out all the exceptions, everything, then finished it, then moved to the next one. That's the model the programmer has of that code. And that's the model your machine has to preserve when reporting exceptions. So everything, so you know that when you report an exception on instruction, all the earlier instructions are finished without any exceptions. They're done, right? And that's the model. And all the state change has to be done as well. So the way you implement this, the second thing is that's exceptions. The other one is interrupts. Now, interrupts are easier, like I mentioned, because they're not related to the program that's running. They're going to cause you to jump off somewhere else and just come back and resume this program. So they're actually easy. You can handle them anywhere in the pipeline. So they're actually an easy case. Let's just skip that for now. So let's go back to this exception reporting problem. And so the real trick here is quite simple. And the idea is to come up with the notion of a commit point in the pipeline. So as instructions execute, they flow down the pipeline and write back the results. And the way we designed our simple RISC pipeline has this property that you've only actually changed the machine state right at the end. So in the write back stage, you update the register file. At the end of the memory stage, you update the data memory. But prior to that, you haven't changed the state of the machine. You can bypass and use values before they're written back. But you haven't actually changed the state of the machine, so you can just blow it all away, the instructions in flight, without changing the state of the machine. So there's some point in the pipeline, which is the commit point. And once the instruction passes that point, it kind of irrevocably updates the architectural state. It's kind of written back, it's done, you can't undo it, right? That's the commit point. And the idea here is what we can do is save any exceptions that show up as the instruction moves down the pipeline and just shift them down the pipeline till you get to the commit point. At the commit point, you know that any older instruction has already committed, and if it had exceptions, you would have taken them, right? And all the newer instructions are behind you in the pipeline. You can just blow them away. And all you worry about is reporting the exception on this instruction that's just crossing the commit finish line, right? You finally, everything else before it is done. This has finally got to the end of the pipeline. It's about to write back. If that's an exception, that's when you report it. And also the nice thing there is it won't have updated the machine state. So the general idea is if I find an exception here, I hold on to it, and I keep going. So the instruction just keeps going down the pipeline because some older instruction may be in the pipeline, and in a few cycles may report an exception that you should handle first, right? So you defer handling the exceptions, shift them down until you get to the end, and only at this point actually take the trap. And so that's also a convenient place to bring in the interrupts from outside, so you can handle those there as well. Yep. Right, so that's a good question. So the question is, well, if that first one was a legal PC, and you keep going, all those later instructions are going to be at some weird PC. You're going to get multiple PC exceptions. Well, the answer is you only report the one exception on this instruction, and you'll just flush the pipeline. So you have this commit point, and so when you detect at this point that there was an exception, you kill the write back, so you disable writes to the register file, you disable writes to the memory, and you replace all these with no-ops. So you turn all those instructions in flight into no-ops. They kind of disappear. And the last piece is that you change the program counter to now be the program counter of the trap handler, right? So you flush the pipeline of all the instructions behind you, some of which may be doing weird things because that first instruction did something weird. But none of those weird things can affect the state of your machine. There may be some weird bypassing and values being calculated and exceptions being thrown, but they don't matter. All that matters is what's committed, right? So you can have all this activity in the machine, doesn't really matter. When you get to the end, you look at the oldest instruction that has an exception. That's the one that you'll take. You'll flush the pipeline, and You won't commit that instruction that takes the trap. You want to write its results back, and then you'll inject the new PC of the trap handler and start running at the trap handler address. So that's how the machine takes the trap. Okay, so there is this little subtlety about reporting the exceptions in program order. And historically, people have tried doing tricks of saving some of this hardware so they don't have to report things in order, but it just causes a mess for software that's very hard to recover from. So basically, every machine now does precise traps. Okay, so this is just really saying that in text. So let's just look at what happens in time, so the pipeline diagram. So if you have a few instructions flowing down the pipeline, say that first one causes an add, causes an overflow. Let me just fill this in a little. So at this point, these 4 instructions in flight are different. This is time running along here. This is stepping down the pipeline stages. Right? At this point, there's 4 instructions in flight, and then you detect an overflow here. You're going to jump straight to trap handler code once you detect this. So basically, this is going to kill this instruction, and these ones are going to get killed and replaced by bubbles. And then you're going to jump to this trap handler code. So it's as if these instructions were never executed. Actually, all of these. And this trap handler is going to have a register pointing at address 96 saying, instruction 96 is the one that caused the problem, and that's what you need to handle in the trap handler. Okay, so the reason we cover interrupts and traps is that this is a necessary precursor to supporting virtual memory in your systems. And when you have a virtual memory system, the most common kind of trap is one where the page isn't resident in memory, and you have to go out to disk to bring it in. And you have to handle that precisely because you want to resume the program once you reloaded that page from disk. Okay, so we're going to talk about, any questions on trap handling before I move on? Yep. Yes, so external interrupts, they're kind of just fed in here. So that was just a design choice. That's not so external interrupts, you have some choice about when you take them. Because it's some external event, you just have to get to them sometime, but not right now in this particular instruction. And I just, my design choice here was at the same point I'm considering exceptions for these instructions, I'll also look at the interrupts. And so notice when you take an interrupt, you have to choose an instruction to interrupt. You say, well, I'm going to interrupt this instruction. It wasn't responsible for the interrupt. It just happened to be the victim that was in the pipeline when the interrupt happened. But you have to report some program counter to the trap handler so it knows where to jump back to resume. So in this case, I'm just saying whichever instruction is in the memory stage, if there's no exceptions but there's an interrupt, I'm going to go service the interrupt and mark the PC of this instruction as being where you need to resume to after you've done with the trap handler for the interrupt. So notice that as I'm executing these instructions, I'm pushing down this field that describes the exception, and also I'm pushing down the program counter. And these registers are the special registers that get written if an exception happened, and the trap handler can read those registers back and say, what was the PC instruction that caused the exception, and why did I get an exception there? Was it interrupt? Was it an overflow? Was it legal? And that's held in this register that's called the cause register in the MIPS ISA. Yeah, I forgot to go through this. So another detail is that when you get multiple exceptions, like one instruction here may get a bad PC address, fetches something from memory that's illegal, gets an illegal opcode. So one instruction going down the pipeline may get an exception at every stage. What you have to do is remember the first thing that went wrong with that instruction and report that, because that was the root cause, right? So if I got a bad PC address, as you go down these pipe stages, if you already have an exception, you ignore any further exceptions and just keep the original one and pass it along, right? So at this end, you'd report there was a PC exception. You ignore anything else that happens. So as soon as one exception happens to that one instruction, you remember that first exception as it moves down the pipeline, ignore any others, and that's the one you report. Okay? So that's another bit of detail to get right. So you want to report the first exception for a given instruction, but you want to report exceptions on the oldest instruction in the pipeline. Right, you want to report the first exception on the oldest instruction in the pipeline. Okay. Any more questions about interrupts and traps? Okay. So let's go on and talk about virtual memory. So, just refresh your memory. Like back in the ancient days, all machines were basically bare machines. So you sat down in front of the computer and you were the sole person running on that computer. You had access to everything on the machine. There was no such thing as virtual memory. There was just physical memory. Every address your program generated was an actual, address that addressed some RAM chips inside, or in the old days, some magnetic cores inside the memory system. So it was very much bare metal. One program ran complete control of the entire machine. And so those addresses, we call those physical addresses. They correspond to, physical devices in the machine. Actually, you can actually watch the signals on a scope and see those addresses go by. Those are the physical addresses inside the machine. So original machines are just all bare metal. One program ran at a time. And so the only kind of address is a physical address. It's kind of a real address. It's really wired to the memory chips inside the machine. These days, the main memory is DRAM, and so that physical addresses generated by the PC go to the cache. When you get a miss, the physical addresses go out to the memory controller. It then reads and writes the lines from DRAM, brings that into the cache, and all of these are physical addresses. So everything in the machine is a physical address. It's a pretty simple, easy setup. This is a bare machine, what we call a bare machine. Now, over time, people realized that they built these big computers, they're very expensive, and once they made that transition to making them all electronic, remember this was the big innovation with the stored program computer. Instead of having to have patch cables and switches to program the machine, which took a few days, and then the program would run for 10 seconds, and you spend another few days reprogramming it. If you could actually store programs as data, you could reprogram the machine very quickly. So now programmers were running really fast, but the problem now wasn't programming the machine, it was I.O. Your I.O. was still mechanical. You had printers and card readers and punches. And so now the program would spend many minutes reading data into the memory, a few seconds computing, then spend minutes waiting to produce output on a line printer or something like that. So what people realized was the CPU itself was being very poorly utilized. If you just ran one program at a time, it would sit there doing I.O., and the CPU was basically idle. And remember, this was a very expensive CPU in the day. So what people soon realized was they could get more utilization by putting more than one program on the machine at the same time, so multi-programming. So if we're on two jobs, while one of them is doing I.O., I can use the CPU to do the compute for a second job, and so on. You could stack more jobs on the machine. The idea is it would overlap compute and I.O. to get a big benefit. Now the problem is, it's not just one programmer now. You have two different jobs running, and you want those jobs to be independent of each other, and you want them to think they both have the machine to themselves in terms of a bug in the other program doesn't affect my program. That would be, it's bad enough dealing with your own bugs, but dealing with bugs that are caused by some other program running at the same time in the machine, there's really no way to deal with that. So in order to support having multiple programs running at the same time on the machine, there's two basic things you need. One is translation, the other one is protection. So translation just says, when I generate an address, say I generate address 0, I don't want to have that actually be physical address 0, because that means that a separate program that runs, a different program that runs, can't also use address 0. And we both like to have address 0, right? Both programs would like to think they have an address 0. So translation basically takes the virtual address that the program generates and translates it to a physical address so that this program thinks it has a segment starting at 0 going up to some distance, some length, and this program too also has address 0, but it starts here in physical memory going on for some extent. So there's a base register here that you set that says where does program 2's address 0 map to in the physical memory space. Excuse me. So that gives you this location independence that you can map the program in. Excuse me. And run it from any location at any place in the physical memory. And you can have multiple programs stacked up, all of them thinking they have their own unique address 0. And the second thing is protection, and that means that when I'm running program 1, all it can access is this portion of memory. It cannot access anything else, including program 2's memory or the memory for the operating system. So I'm going to isolate the program, so when it's running, it's limited in what it can touch. And this prevents bugs from one program corrupting data from a different program. Well, these days you worry about security. This program reading data that it shouldn't be reading from the other program. Now, to support this, a question? Oh, yes. The question is, how do you know how much program you need? So back in the old days, you'd have to state, like, here's my job, here's my stack of punch cards. This job's going to need, 12 kilobytes of RAM or whatever, and that's what you get during your run. If you exceed it, you would die. We'll get to like modern systems that have a more flexible way of handling this memory allocation. Right? But back in the old days, it was all batch jobs, and you basically had to say how much space you were going to use. And usually at different queues, so the more memory you said you're going to use, the less frequently it would run your job. Like if you could fit along with other jobs, you could more likely get to run. So you had to balance between how much memory do I need and the likelihood of me getting to run this big program. The other thing that happens, though, is when I have two programs sharing the CPU, some mechanism has to share the CPU. So you have to decide, how do I switch when this one's doing I/O? How do I switch to run the other one and back again? And the thing that's doing the switching better not be under control of one of the users, because they'll just steal all the CPU cycles, right? So that's when you get the notion of needing an operating system that is just some more software. It's just another program running on the system. But it's a special program that has more privilege than the regular user programs, and it's used to multiplex the CPU between those different user programs, right? So this operating system is just more code sitting there. It has access to a few more bits of state in the CPU. We'll talk about, we've seen some of those already. The cause and the error PC that reports the exceptions, that's only visible to the operating system code. And so the CPU now has a bit of state, so one bit that tells you, am I in user mode or supervisor mode? So when you're in supervisor mode, you can touch all these extra things inside the machine. When I'm in user mode, I'm just constrained to running inside my little segment, and I cannot see all these additional extra registers in the machine. So you protect the machine against bad user programs. Okay, so now this notion of wanting multi-programming so I could get better utilization of my CPU when jobs are doing I/O, that led to the development of operating systems. And that operating system's main job was just to switch between the jobs. And so when one of the jobs did a request for I/O that would go to the operating system, it would schedule the I/O on the device, turn that job off, set the I/O device running, then start running the second job on the CPU until there's some interrupt from the device saying, I'm finished with that I/O. Then I go back to the first program again. So this operating system is a software that manages all that switching. Now, the simplest kind of translation is kind of like I've been talking about, is this what we call simple base and bounds. And we like to start with this, even though it's not used in many systems today. It's a very easy way of understanding the concepts of translation and interrupts and protection. So this system just needs two extra registers inside the machine, a base register and a bound register. And these are privileged registers that only the supervisor can access. Right, so that program, when you're in supervisor mode, running the supervisor code in the operating system, and when you start to launch a new job, the supervisor is going to write these two registers, giving the base of the user code segment and the bound, which is how big the segment is. And then the supervisor will load the code into that segment, and then at some point it's going to jump to user mode. So there's usually a special instruction that says, now start running in user mode, leave the supervisor, jump to user mode at this program counter. Then the CPU switches, starts running in user mode, and it's inside that protected segment. So at that point, all the addresses that the program generates, these logical addresses, are translated to a physical address just by adding the base register to them. So you have this one number here, you add it to the logical address, and that gives you the physical address out in physical memory. Okay. At the same time, in parallel with adding this on, you also check how big is that address, right? So you go from 0 to some maximum number, and it checks to make sure that you don't try and generate an address outside that range. If you do, you get a protection violation. And this is what's called a segment fault, seg fault. That name still lives on, even though we don't use segments anymore. But that would be a bounds violation. I tried to access something outside of scope of the machine. So important to note, these registers are only visible when you're in supervisor mode. The user program doesn't know they're there, right? It just thinks it has this whole machine, but only this much memory inside that machine. Okay. One little tweak that was done on this scheme is to have a separate base and bound for program fetches, instruction fetches versus data memory accesses. And so the idea is you have one base and bound is added to the program counter here, and a separate base and bound is used for the data segment. And so why would you want the two segments? What would be the advantage? Anybody think of anything offhand? Why not just have one segment? Why have two separate segments? Say, 100 users logged into a machine. Yep. Reduce fragmentation. It might do. You could put the program in some hole and the data in some other hole, so they would fit in two smaller holes. That'd be smaller than if you had to put all of it in one contiguous one, kind of. That's not the main reason, but that's a possible answer, yeah. Yep. Yeah, why would you want to separate the program from the data? Yep. Oh, okay. Right, it's what you can have is you can have one copy of the program in memory, and you could have several users using the same program. You only have one copy of the text. So you could have, say, 100 people logged in using SSH. You'd have one copy of the SSH binary in memory. And all the data would be separate for each user. So you could reuse the code across all the different instances of that same program, right? So if you're running some kind of server application, often people use the same program, like a shell or something, and you just have one copy of the code and just have different data sections, right? That's the main reason. So this actually scheme is what was used on all the Cray vector supercomputers, like all the fastest machines in the world. This is all they had for their memory protection translation because it's really simple and really fast, unlike the schemes we'll talk about later. But this is actually was used until pretty recently on the big machines. So how does this fit in the pipeline of the processor? So let's think about how you implement this stuff. And basically, it's a small addition to the pipeline. So where you generate a program counter here, you're just now going to add this value on before you go to the instruction cache. And the bound, you're just going to check this against that address and just raise an exception if there's a bounds violation. Okay, so just a couple bits of hardware you add to the machine. And the same over here for the data address. Yep. It's a question? Okay, so you just add, just an adder for each base and then a comparator for each bound at these 2 points in the machine pipeline. So now let's think about the types of addresses in the machine. So the address here is a logical address or virtual address. And then it gets translated after the add, this becomes a physical address. The same over here. The memory, the addresses that the programmer sees in user mode, those are all logical addresses, right? They don't mean anything until you add the base and convert it to a physical address, which is actually a location in the memory, right? So here you just adds, every time you go to the data memory, you're going to add this base first to get a physical address. And notice the caches are just talking to the memory controller using physical addresses as before, right? So you're doing that virtual to physical translation right before you get to the cache, right? And the cache just works the same way. It's just caching physical addresses. Okay. All right. So now talking about fragmentation. So one of the problems with this kind of machine is this notion of fragmentation. So say I start with a set of jobs running on the machine. This is an old slide, so these are pretty small jobs, 16 kilobytes, 24 kilobytes, 32 kilobytes. And there's some holes, pieces of memory I'm not using. As some more users arrive, you start filling in, finding a place where their job will fit in the memory space. But you get this fragmentation, which is the holes between those allocations, right, that's unused. And so what can happen is you end up with lots of little holes that collectively are big enough to run the next program, but because they're not contiguous, you can't allocate the whole segment, right? You've got this fragmentation problem. Your memory's being split up into lots of little pieces, right? And so this was a problem. So how do you solve this problem on these machines? How would you get rid of the gaps? How would you coalesce them? How could you do that? Yep. I have to speak louder, sorry. Remember that all the memory for one process has to be contiguous, and you allocate these as you're going. Right, that's the question.
Do you connect the free segments and then relocate the already occupied?
Right, so basically what you have to do is basically move all the data around. So you have to basically compact it occasionally, right? So you might remember, you may still, be old enough to remember when you had to defrag your disk drive, right? Your disk drive gets fragmented, and you have to pack all the files together at one end of memory. You kind of do the same thing in memory here, where you take all the active, you've got to stop the whole machine and just copy all these data segments down to compact them all next to each other to put all the free memory at one end of the machine. Now, the thing to realize is the user program doesn't care that you did that because it never touches the physical addresses directly, right? So when you move all that data in physical memory, when you restart the user program, you just have to change the base address to the new base address, right? And everything else, as far as the program is concerned, is the same, right? So remember, when the user stores a pointer in its data memory, that pointer is a logical address. So whenever that user program retrieves that pointer, does something with it, it's always going to have the base address added to it before it actually touches physical memory, right? So you can just simply copy the whole segment around and just change the base address to relocate that user program anywhere in the memory. So occasionally, if you got fragmentation, you just have to, used to call this burping the machine. You're taking all the air bubbles out, just compacting the machine and freeing up all the memory at one end. But that's pretty expensive because you're copying a lot of memory around. All the live memory in your machine, you have to copy around. So you do that very carefully. And this was a big issue with this kind of simple translation scheme. So this was the motivation for people developing paged memory systems, which is what we're going to talk about the rest of today. So the idea here is instead of having single variable size segments that you try and allocate in the memory, you take all of memory and break it up into fixed size chunks we call pages. And what we're going to do is translate each page independently. So any page of logical addresses it's like it has its own separate base register that it can be any page in the physical memory. So any page of virtual address range can live any page in physical memory. And the nice thing here is then you can easily, any program that comes along, you just care about how many pages it needs. You don't care about where those pages are because you can find any free pages anywhere and just point at the free pages and populate that virtual address space without having to move all the data for the existing programs. Okay, so any given user's address space here can be mapped to different pages. The key thing is that the pages are fixed size. The standard size these days is 4 kilobytes, right? So there's 4 kilobytes in a page. You take all your memory, so you have a 4 gigabyte machine. You have 1 million pages, each of 4K, and you can flexibly allocate those to different jobs as they come and go. It also makes it easier if a job needs to grow its memory space. You can easily extend its virtual address space and then just find more pages to map the extra memory into, right? So the big advantage of this scheme is you get rid of that fragmentation, the external fragmentation, and you have this very flexible allocation. So if you look at what happens to so now when you take the address from the user program, the logical address, you split it up into two pieces. There's an offset, which is just the byte within the page. And that's the same whether it's virtual or physical address. It just tells you within a 4 kilobyte page, which byte within that page. Just like when we had the cache line, right, you had a byte offset that says which byte within the line. Right, and that was kind of independent of all the tag checks and stuff. The same here, you have a page offset that says which byte within the page. The top part of the address, the high bits, tell you the page number. So what we have to do is take every virtual page number and translate it into a physical page number. So it's almost like every page has its own independent base register, right? That gives you that translation. For this virtual address range, where does it map to in this physical address memory, in this physical memory? So that mapping is held in what's called a page table. And you have a separate one for every program that's running on the machine. So say you have, in his case, 3 users running different programs. Each one of them can have their own virtual address page 1. You indirect through a page table that tells you, whereas this guy's page 1 is here, this guy's page 1 is down here, this guy's page 1 is over here, right? So they can be arbitrarily mixed. There's these separate per page indirection entries. So there's one entry for every page in the user space. And every user has an independent page table that describes the mapping for that program. So the other thing to realize is inside the physical memory of your machine, as well as the user data, there's all the operating system as well. So the operating system just lives in the physical memory too, and it reserves a set of pages for its own code and its own data, right? So the operating system up here has its own pages. So these page tables are only accessed by the supervisor in supervisor mode, right? So it gets to control how the user touches memory, which pieces of memory it can touch, right? And so that's all handled by the operating system. So these page tables are these structures that provide this indirection. Given this virtual address range, where should I map it to in the physical range? And so the big question is, where do those page tables live? If you start thinking about this, if you have 4 kilobyte pages and a 4 gigabyte address space, you have 1 million pages, right? So that's quite a large set of, that's like 1 million base registers, right? From one process. You may have many processes running. So it's kind of a big structure. You don't really want to keep that inside the CPU. So really, they just kept in main memory. So the idea is you're going to use physical memory to also hold the page tables. So remember, physical memory is holding the user program, the user data. It's holding the OS program, the OS data. It's also holding these tables that give you the mapping from virtual to physical addresses. So the page tables also live in the physical memory. So the problem here now is, wait a minute, that means that every time I go to touch memory from my user program, I have to first go touch memory to find out where it is, right? So I have this indirection, right? So that's an issue. Excuse me. So let's see what that looks like. So the page tables are just stored in memory as well. So I generate a virtual address, I go to memory, I figure out where is this page? Oh, it's over here, okay? And now I add the offset and pull the byte out of this physical memory page. But every single memory access has to indirect via these page tables that are held in memory. So that seems pretty bad. You've doubled the number of memory references the program needs to make. And we know this memory is the slowest thing in a system, so that seems bad. So we'll get about how to solve that in a minute. You can tell us building up the suspense. How are we going to solve this problem? A minute's trivia, though. So the midterm 2 scores are up. So the regrade request deadline is basically midnight on Sunday. So after that, we all assume you're happy with your grade, or as happy as you can be with your grade. Just to look at the score distribution, as again, there's no students in the class who get a perfect distribution every time. People did pretty well. They got a mean of 25, roughly, out of 45. A good spread across the whole range. Okay, so this is on the Piazza, so you can take a look at this and figure out where you are. So to remind you about the final that's coming up, we do this. The final, there's going to be marked midterm 1, midterm 2 sections, as well as the post-midterm 2 sections. And you can clobber your midterm scores with the appropriate pieces of the final, right? So if you really messed up on the midterm, you have a second chance to do better on the final. Well, the final thing is Project 4. We extended the due date to Wednesday, April 29th. For the part 1 of that project. Okay. All right, so question? Sorry, say again? Will part 2 still be doing the same day? Yes. Okay, just finally in the news, a few days ago, it turned out it was the 50th anniversary of Moore's Law. So it's actually 50 years since Gordon Moore wrote this paper that appeared in this electronics magazine. And so this is from the abstract of the paper. The unit cost falling as the number of components per circuit rises. By 1975, economics may dictate squeezing as many as 65,000 components on single silicon chips. So these days we're up into the 100 billion components, but he was looking ahead to, the end of the decade, 65,000 components on a single chip. And what's interesting, if you go read his paper, old Moore's Law was based on 5 data points, right? This is the graph. So he basically took a bit of, log linear paper, plotted 1, 2, 3, 4, 5 points, then drew a straight line up and said. And what's amazing is the whole industry followed him, right? So, he said this is what's going to happen. Everybody's like, okay, well, if our competitor's going to do that, we better do that too. And everybody's thinking everybody else is going to do it. And that shows a self-fulfilling prophecy. He kind of said, this is how fast things are going to go. But everybody followed it, right? Except we're starting to finally get into the atomic limits of that. Okay, let's take a 2-minute break. Okay, let's get going again. So I want to take you back to a very early machine to explain a new idea we haven't talked about so far, which is virtual memory demand paging. So today we just focused on, so far, translation and protection. So taking a virtual address and changing it to point to a different physical address in the machine. And you can do that either with segments or with pages. And there's also protection, not allowing a user program to touch anything except a certain, predetermined set of memory ranges, address ranges. Now, what people soon realized was another thing you could do is if you had these mechanisms, you could support virtual memory. And the idea here is to expand the seeming size of your machine using the idea of a memory hierarchy. So we're going to use main memory as a cache for disk storage. So you can pretend as if you had more DRAM in your system by using disk as a backup. And the idea is you can automatically bring pages to and from the disk into your main memory system now, and the user will have the illusion now of having a much bigger available memory system than you actually have physical parts for. Right? And this idea goes back to this machine Atlas, which was built in Manchester, UK. And this is a very old machine. The hardware there had the main memory there was only 32 pages of main memory. That's all they had space for, and only 512 words on each page. But yeah, the secondary storage, which wasn't actually a disk, it was a thing called a drum. So a drum was like a big cylinder that rotated round, and the surface was magnetic, and it had an individual head on each track of the drum. So it's kind of parallel readout, but quite limited capacity. This was the sort of high-speed secondary storage of the time. And this had, 32 times 6 pages, so quite a bit more capacity than the central memory. So they used the primary memory as a cache for the secondary memory, the disk storage, the drum storage. So it's appeared to the user as if they had, 32 times 6 times 512 words of main memory, but only, 1/6 of it could actually be resident in the high-speed electronic memory at any time. And so this is kind of how the machine worked. The address would come in, and every page in main memory actually had a hardware register attached with a page address register. And you would search this address in these registers, and when you got a match, you would know that, this address is resident in the machine, and I can just access it from the physical main memory. But if you did a search here and you didn't find that virtual address, you would say, it's not resident in main memory, it's out on the drum, I have to go fetch it from the drum. Okay, so then the system would invoke the operating system. It would take what's called a page fault. I don't have this page in main memory. You would stop execution. You take a trap, jump to a trap handler, jump into the operating system. The operating system would find where that page was on the drum. It would have to do a policy, as with a cache. Once you bring something in, you're going to have to kick something out. So you have to pick a victim that's going to be written back to the drum to make space for the new page coming in. Okay, so it would write out an old page, bring in the new page, and then you would restart the program. And so the program wouldn't know that, apart from time taken, functionally it would be the same as if everything was built from main memory, right? So this is using a combination of the hardware plus the operating system to implement something like a cache, but now one level out where it's main memory talking to disk. So this is the concept of virtual memory. So this is just going through what they did on Atlas. They would actually keep some, there'd be one free page in main memory that as soon as they got a miss, you would immediately fetch the thing you were waiting on into that free page. And the idea was in the background, you pick a victim to write out. So you wouldn't have to wait to write out a victim and read in the next one. You kind of have one page ready to go that you could load straight into. Another thing they did was, because it's a rotating drum, the latency depended on which, was it going to come under the head next? So you have to wait for the mechanical rotation time. So it actually picked free pages to write back to based on where the drum was at that point in time. Then they would write it back, and update the table it would keep. So the operating system would know where each page of virtual memory resided on the drum, so it could find it again later. So, fast forwarding to today's machines, we do this a little differently. The idea is each entry in the page table that we use to do translation in a page-based system, it has some extra status bits that indicate whether that page is currently resident in main memory or if it's swapped out to disk right now. And so, this is your virtual address coming from the CPU. There's an offset that you just directly push through as the byte offset within the page. There's the virtual page number, which you're going to index into this table to find the corresponding physical page number, right? So this is doing the indexing. Here's the virtual address. I index into this page table. Here's a physical page number, points at the base address of that page in memory. But in addition to the physical page number, there's also some extra status bits. And one of those bits tells you, well, it's not actually resident, it's a disk. It's on disk. We have a disk page number, which says where on disk is that page. So now if you do an access, you indirect through this page table, and you find out it's on disk, you'll take a trap into the operating system. The operating system will figure out what's going on. It'll look at the cause register that will say this was a page fault. It will look at the an extra register will tell it which address caused the page fault. It will then go look in the page table and figure out where on disk is that page. It will then schedule bringing that page in. It will update the page table to point to that page in memory. It will find some other page to evict and write back. And then it will restart the program back at that exception PC, but now with the memory loaded, so the next time you go indirect, you'll find it's resident in main memory, and you just keep going, right? So the page faults are continually happening on the side with the operating system bringing things in and out from the secondary storage. So one other thing is the way this is done in the machine, you have some register in the machine for the currently running program. You need to keep track of where is its page table in memory. So there's what's called a page table base register. That is just a hardware register the supervisor loads. It's only accessible to the supervisor code, and that tells the hardware where to find the page tables for the currently running user program. So you know where to go, look in memory to do this indirection, look up this table. So every user program, as you switch between one program and another program running on the machine, when you're multi-programming, what the operating system is doing is switching that page table base register to point at different page tables in the memory. Now this picture, I've just drawn this as what's called a linear page table, right? So there's just one big page table, and I just take the high bits of the address, index into here to find the physical page number. So it's just a very simple 1D structure. The problem is that if you look at with a 32-bit address space and 4 kilobyte pages, we're going to have a million entries in that page table. There's a million pages, right? 1 meg pages. And each of those entries has to store a physical page number, which is going to be roughly, and a few status bits. So that's going to be a bit less than 32 bits, but so let's round it up to 32 bits of storage for every entry in that page table. So a million of those is going to cost you 4 megabytes. So every user program would need 4 megabytes of storage to hold a linear page table. You might think, well, that's not so bad, 4 megs. My programs are usually way bigger than that. But it takes a long time just to initialize that and to play with it. So for the operating system to manipulate it. So even if you don't worry about the capacity of that it takes up, it's actually a lot of runtime. Now, if you go to bigger systems like a 64-bit address space, like most of your machines and even your phones now, most of them are 64-bit, you can't really do a linear page table because you would need like terabytes, like tens of terabytes of storage to hold the linear page table. So it's just not feasible to have this one-dimensional structure that you index with all of the virtual page number at one time. It's just not practical to do. The real sort of insight that makes this all work is that, well, not every program uses all of the virtual address space. Not every program needs all 4 gigabytes on a 32-bit machine. And on a 64-bit machine, no program uses all of the 64-bit address space. They all use a small fraction of the available address space. So you only need to represent the translations for the portion of address space you're actually using, right? So you need a slightly more sophisticated technique, but this can dramatically cut back the amount of space you need for these page tables. And a general thing that's used in nearly all systems is what's called a hierarchical page table. And so for a 32-bit system, you can break you have a 12-bit offset, then you have a 20-bit virtual page number. You can break that into two 10-bit level 1 and level 2 index. And the idea is now you have the page table base register inside the processor. This is the thing that the supervisor writes to tell it where the page tables are. That now points to a level 1 page table that in turn points to level 2 page tables. And so you take 10 bits of this, the type 10 bits of the address, you use those to index into level 1 page table. That tells you the pointer to the base of the level 2 page table. You then take the lower 10 bits here of the virtual page number, index into the level 2 page table to actually get the base of the physical page in memory, and then finally use the offset just to get the byte within the page. So now you do 2 indirections through memory, not just one. Okay, so now you've taken every request the user does, you're now going to do 3 times the number of memory references. Once to level 1, then to find level 2, And the advantage of the hierarchical one is that if there's portions of the address space you're not using, you don't need a level 2 page table there. So these grayed out sections, this whole piece here is not present. There's no level 2. And these are pretty big. So how big are the regions that each one of these entries corresponds to? How much virtual address space is this blacked out entry? How big is that hole that I've created in the virtual address space? How many bytes do I not have to map? So each entry in the level 1 page table, how much does it map? Sorry? 4 bytes? So the pages are 4 kilobytes, right? So one of these entries corresponds to a 4 kilobyte region, right? What does one of these entries correspond to? How big a region? Yep. Right, it's 2 to the 22. So 4 megabytes, right? That's right. So basically this 10 bits points at one of these entries, and this entry tells you everything about the bottom 22 bits, right? So you take the next 10 bits to index here, find this entry, but all these entries are pointed to from this entry, right? So this entry points here. There's 1024 entries here of 4 kilobytes each, so that's a 4 megabyte region, right? So each one of those top entries is 4 megabytes. So every part of the address space where there's 4 megabytes, I'm not using any of it. I don't need a level 2 page table. I just keep this blank and say it's not accessible, right? So if I start indexing down here and I find an empty page here, I immediately take a fault saying, segmentation fault. You shouldn't be touching that memory. So the operating system doesn't have to provide the mappings for the whole 4 gigabyte range. It just provides the mapping for the portions of it that you're using, right? And so it can leave out. There's only one of these level 1 page tables for the whole process, and you just create as many level 2s as you need instead of creating everything. If you flattened out all level 2s and stacked them, they'd be the linear page table. But basically, you can just leave out ones that you don't need here, right? So you only represent the pieces you need. So it's kind of a sparse data structure, right? So that's how the page table is represented. So in a 32-bit system, it's quite common to have 2 levels, sometimes 3. 64-bit systems, you often have 3 or 4 or 5 levels of hierarchy in the page table structure like this. Okay, so that reduces the capacity of these tables. You need less space to hold them. You need less time to initialize them when you're starting up a process. But the problem that should be in the back of your head is, well, wait a minute, I'm now going to memory 3 times as often as on the bare machine, right? I have to indirect through 2 levels of page table. On a 64-bit machine, it might be 4 or 5 levels of page table before I get to where the thing really is in physical memory. That seems like an unacceptable slowdown, right? It's just showing the 2-level page table. So here's user 1. He has 1 level 1 page table plus some number of level 2 page tables. Here's user 2. They have a separate level 1 page table plus their own level 2 page tables, and also some physical memory in there. So the real problem here is you want to, ideally in your memory system, you want to do all this in one cycle. I don't indirect 3 times through memory just to load a value from my cache, right? So I want to do everything go from the virtual page number directly to the physical page number in 1 clock cycle, right? That's what I really want to do. And at the same time as doing this translation, I also want to do protection checks. Like, am I allowed to touch this page? Is it user mode only, or is it just privileged code can access this? Can I read it? Can I write it? All those kind of protection checks. You want to do that in 1 cycle inside the CPU pipeline. So this is kind of what we're trying to do, is take the VPN piece of the address, translate it to the PPN, physical page number. The offset just falls right through. That doesn't get changed. And we do this for every single instruction access, every single data access that the machine is running, right? And we need to do this fast in 1 cycle. Now, the way we do this is we take advantage of one of the great ideas in architecture, right? So if memory references have locality, the address translations are also going to have locality, right? So which addresses you're using, you're going to reuse the same addresses, you're going to use nearby addresses. So the idea is to build a cache for address translations. So we're going to build a cache, and the purpose of this cache is to cache the mapping from a virtual address to a physical address. And that's what a address translation cache does, except thanks to IBM, they're not called address translation caches, which is the obvious name. They're instead called translation look-aside buffers, right? But they're actually address translation caches, right? But TLB has become so embedded. IBM was the first one to ship commercial implementations of this in quantity, so I guess their name stuck in this case. But it really is an address translation cache. It's called a TLB though, translation look-aside buffer. So the basic idea is you build a cache which is usually associative, fully associative. You take the virtual page number, you search across all the entries in the cache, and if you get a hit, you read out the physical page number. Right, so in one cycle, you don't have to do that walk through the page tables, you just instantly get the physical page number. Right, and this relies on there being locality, so a small number of TLB entries will capture a lot of the memory accesses you make in a program, right? So this is a cache, so you get a miss occasionally. You try to access an address that isn't in the TLB, and you'll get what's called a TLB miss, right? So this is just address translation cache miss. I tried to translate an address that wasn't in the cache, right? So if you get a TLB miss, what you now have to do is actually do a page table walk. So when you get a cache miss, you just go to memory and copy the data from that address in memory. But this is caching the translations. You actually have to go walk through that data structure to find the mapping from the VPN to the PPN. And then you cache the result of that walk in the address translation cache. The refill process is a bit more complicated than a regular cache, right? You have to actually do the page table walk. And that page table walk is actually usually done in hardware these days. So just talk about the TLB structure. So common level 1 TLBs and processors these days are something like 32 to 128 entries in there. They usually map a page, 4 kilobytes. So there's from a 4 kilobyte virtual page, the virtual page number of a 4 kilobyte page is mapped to the physical page number. They're usually highly associative, if not fully associative. So it turns out there's less spatial locality at the page level because you kind of soaked it all up. It's because they're much coarser grains. It's much less likely that you'll access neighboring pages than neighboring bytes within a page. And so basically, to avoid conflicts, you tend to have a fully associative TLB. Sometimes, and increasingly, systems now have a level 2 TLB, and that is often not just a simple level 2, a little more complicated. You should take 152 to find out more about virtual machines and how they work. But the level 1 TLBs are pretty good to capture most of the references, so 32 to 120 entries. The replacement policy, because they're large and they're fully associative, you cannot implement LRU directly. Like trying to do true LRU on 64 entries is complicated, complex, expensive. So usually you have some much simpler scheme like random or FIFO. FIFO is pretty common. It's just a pointer that points at an entry in the TLB. When you get a miss, that's the entry that gets kicked out. And every time you do an access, they may bump the pointer and it just might spin around. It's kind of like Russian roulette. The other guy is going to go next. And it turns out that works out okay because if you get it wrong, you just bring that thing in on the next miss and kick out the guy below you. Another design parameter of these TLBs is whether they remember which virtual address space they're for. So remember that when you're running on a machine with multiple programs, there are many virtual address spaces, each with their own page table. And at any one time, the operating system runs a program and loads the page table base register to point to the base of the virtual address space for that current process. When you switch between processes, you just change that page table base register. However, the TLB is caching translations from a virtual address to physical address. You have to make sure you don't get the other guy's virtual to physical address translations. And one simple scheme is every time you swap between two different jobs, you flush the entire TLB. Just make it all invalid and start again. And in fact, all the x86 processors used to do this. And it was kind of a performance problem. Bigger mainframes and bigger workstations. What they'll do is the TLB entries are not only tagged with the virtual page number, but also with another a tag that says which virtual address space am I currently caching. So you may have like 1024 different address spaces you can cache, and they'll be tagged in the TLB as well, so you don't have to flush all the TLB entries as you switch between multiple processes. Right? That's kind of a detail. So one of the design parameters for TLB is how much address space can I cache? It's an address translation cache. How many address translations can I cache? And this concept is called the TLB reach. And the way to think about TLB reach, what is the largest region of virtual address space I can cache in a TLB without an access without getting misses? Right? It's just simply, if you got, say, 64 TLB entries, 4 kilobyte pages, there's one page in each entry, it's just multiplying those out. So you can, 256K would be the answer here. That'd be how much data I can now simultaneously map in a TLB. Now, one of the problems people experience sometimes in computers is that when they're running their programs, they have some data set and it should fit in their outer cache. And so they expect to get good performance, and they find they're getting bad performance. And what they're hitting is sometimes the TLBs are designed poorly and they can't actually hold enough address translations to even map the level 3 cache from the system. And so even though the data fits in the level 3 cache, the address translations to access that data don't fit in the TLB. And so you're not getting L3 cache misses, you're getting TLB misses. And that's a problem with insufficient TLB reach, and that's a problem on some commercial designs. And that's the push to provide these level 2 TLBs to give you much greater TLB reach. You can actually use all the, because the caches have got bigger and bigger and bigger, and the cores haven't sort of kept up with in terms of their TLB reach. But increasingly they're adding level 2 TLBs to be able to access all of the level 3 cache without getting TLB misses. Okay, let's sort of flip this back into where do you put this in the processor? How does it fit into the hardware? So basically you can think about it fitting in between the same way that the base and bound stuff fit in the pipeline. The TLB kind of fits in the same place. So you usually have a separate instruction TLB and a data TLB. So instruction TLB looks at the program counter coming in and will convert this, take the VPN of this, convert it to a PPN, then send out the instruction cache. At the same time, it's doing those checks. Do I have a page fault? Is there a protection violation? Or do I just get a TLB miss, right? And those checks are happening at those points in the pipeline. You do that for the PC, for instruction fetches. You do it for the addresses going to the cache as well for data accesses. So the TLB miss is not, you can either do that in hardware or software to refill the TLB. It's usually done in hardware now, and let's just assume that for this course. So what that means is kind of like a cache miss. There's no exception or trap. It's kind of like a cache miss when this TLB gets a TLB miss. It'll then go off to memory and refill itself. And then the program will proceed. But if what you discover is there's a page fault, i.e. the mapping is, the TLB entry is there, but it indicates that that page is currently on disk, then you have to invoke the operating system software to go get the thing from disk, because that's a page fault. Right, so the OS is code that causes a trap. The same with protection violation. You try and access some memory that doesn't exist, you're going to get a page fault. You're going to get a protection violation, which will cause a trap again to the operating system. But TLB misses are usually handled in hardware these days. Okay, so just this is an example from industry. This is a Spark V8 instruction set. And the way they actually define the supervisor of a 3-level page table, even though it's only a 32-bit address space. And they actually added this extra context table. So this kind of walk through this structure is all done in hardware. So you get a TLB miss, the hardware engine inside the CPU walks through this data structure and refills the TLB. So this is an interface between the operating system and the hardware. The user program doesn't care about this. But your operating system has to know the layout of these page tables and how the hardware page table work is going to work, walking through this, because the entries are written by the operating system. The hardware just does the refill and interprets the entries, right? So that's part of the operating system interface, is this page table structure. It's not visible to the user, but the operating system needs to know how all this works. And so just trying to put this together in the hardware with a hardware page table walker. Here's the instruction TLB. If you get a miss, you tell this hardware page table walker, which has this page table base register as an input. It then usually goes through the cache to actually access the page tables. And all this is physical addresses down here. Right, so let's assume that all the page tables are held in physical address memory. This thing just sends out addresses and gets replies back and uses the cache because the page tables also have locality. So you want to use the cache to cache the page tables. Another reason that the page table walker wants to go through the cache is the operating system is updating these values. You want to make sure that the page table walker sees the most recent writes the operating system did, so it looks in the cache. Right, so that's kind of the whole picture of a simple virtual memory hardware system. Oh yeah, and if it's not just a miss, which is handled by the hardware, but it's actually some kind of fault, then you can take a trap, and this will invoke that exception mechanism we talked about at the start of the lecture to actually cause the CPU to jump to the handler. So one other thing, when one of these traps happens, that's a case where you switch the processor from running in user mode to running in supervisor mode. So you're running in user mode, something goes wrong, you jump to the trap handler but set it to supervisor mode. And at that location in your code, there'll be some OS code that will run and do the right thing. And then when it's finished, it has an instruction that jumps back to user mode and turns you back, removes your privileges and restarts at the restart PC. Okay, so kind of putting this all together, the virtual memory system, you get a virtual address comes in, you do a TLB lookup. If you get a hit, it's great. If you get a protection check, it's fine, it's permitted. You just go ahead and send the physical address to the cache. If you get a hit, but you're not supposed to be touching that, you get a fault, and you take a trap. If you do a lookup but you get a miss, you have to do the page table walk. If the page is in memory, you'll just update the TLB and keep going, and just actually replay this instruction. It'll go down this path. If it's not in memory, you take a page fault, the operating system will bring it in again. Right? This is kind of a flowchart of address translation. So the whole goal of this, to summarize, is to give you many users sharing the hardware of the machine. They're sharing the physical memory system. You can just keep the active portion. Even if they allocate a lot of addresses, they only usually touch a portion of it. You just keep that hot data in the DRAM, and the rest can be paged out to disk. So you can cram more jobs on the same machine. You also get this protection between the users, and that's important to let people share these machines. The only cost is you have to provide this translation on every memory reference, but the TLB is a trick to making it happen fast. Okay, so we'll go through this slide, but I'll just say it's a long history of doing this. You just read through this slide. We won't talk about it in this class, but in Project 4, you'll be using Amazon, which runs not just the processes in virtualized, but whole machines. So the virtual machine idea is we pretend you give your whole machine the operating system runs in, but in fact there's another level of virtualization on the outside of that. So we'll be using that in Project 4. Okay.